Right. Oh.
Thank you, guys. Okay, so hello again. Today we are going to finish up everything you need for Chapter 6. So you'll have everything you need to do the homework over the weekend. Might give you an extra day or two anyway, though, since I just wasn't here to make up for that fact. Something wrong?
Oh, yeah.
Okay. You get a paper towel if you need one. Okay. So we are finishing up chapter 6 today, momentum, collisions. The problem we left off on last time is we did the throwing star and log, right? That was an example of an inelastic collision. Today we're going to define that versus an elastic collision and do some elastic collision examples, which will round out everything that you will need to know for the homework. And talk a little bit about explosions and what makes those different from a collision. And I'm about to sneeze. I feel it, but it's not happening.
Bless you.
Thank you in advance. Don't you hate it when you know it's coming, but then it just stops? The feeling stays. Okay, that's gonna happen when I least expect it. So before we get started today, does anyone have any questions? You've been doing the homework, right? So there's also a good chance to ask questions related to the homework before the weekend begins. All right. Well, if no one has anything specific, let's go ahead and get started. We've been talking about momentum and collisions. We worked a very specific collision example with the shuriken hitting the log. This type of collision, where one object sticks into the other, and they then travel as a single object afterwards, is usually referred to as an inelastic collision. I'm trying to enunciate very clearly when I say that. It is an inelastic collision, which means it is not elastic. So, in case before, where the one object joins to the other and they then become one object traveling in unison, that is an inelastic collision because it is not elastic. Why is it not elastic? It doesn't bounce off, that's right. Elastic objects, as we discussed when we were talking about elastic potential energy, an elastic object is able to deform and store energy inside of that deformation and then go back to normal by releasing that energy. But metal and wood aren't really very elastic. Neither of these objects are able to go back to their original shape after the collision. The metal of the shuriken might not deform much, but the wood now has a hole in it. It has permanently deformed due to this interaction, and it's not able to just go back to normal. It didn't store any energy, it's not able to return to its original shape. So these are inelastic objects colliding in an inelastic collision. And in every type of collision, momentum is always conserved because momentum has only one form it can take. But in this type of a collision, the energy in the system, the kinetic energy in the system, is not conserved because energy has lots of different forms it can take in lots of different objects. So, if you look at the energy present in each half of this question, initially, in the first half, where it's just the throwing star moving towards the log, that object has this mass and this velocity. If you solve for its initial kinetic energy, you get about 31 joules. But afterwards, where the two objects are joined and traveling together, they have this total mass and this velocity. If you solve for the kinetic energy of the joint unified system, it's a lot less. There's a lot less energy present. So the momentum was conserved. We used that to solve the question. But the energy, the kinetic energy, was not conserved. it's basically all gone. There's still a little bit, because in order for the log to move, it needs kinetic energy, but most of it is gone. So, in the type of collision that we just did there, the inelastic collision, I've got the types and descriptions written up over here. Objects tend to stick together in an inelastic collision because when they deform, they don't bounce back. They're just stuck. Kinetic energy is not conserved, but momentum is. Momentum has to be because there's nowhere else for it to go. But because energy can take lots of different forms, it's able to go somewhere else in this type of a collision. So the kinetic energy drops. That is the main feature of an inelastic collision. Now, we know that energy cannot be created or destroyed. So the missing 31 joules has to be somewhere. It can't suddenly not exist anymore. It's no longer in a kinetic, observable form within the objects we were just looking at. The energy has to exist, it's just somewhere else. Now, I'm going to create an inelastic collision when I drop this marker onto this tabletop. And I want us all to think together about where the kinetic energy goes in this collision. So, when the marker hit the tabletop, kinetic energy transferred out of the marker, and the tabletop itself didn't move, so not a whole lot of energy went into it. Not in kinetic form, at least. So what types of energies, what places do you think the energy is going in this collision?
So it's going back to the marker?
Some of it is, yes, because even non-elastic objects still bounce a tiny bit. Not a lot, but a little bit. So the marker keeps some of its energy, gets some of it back, starts bouncing upwards at least a tiny bit. Where else does it go? Some of it goes into the table, yes. If I did this enough times, you would eventually be able to feel this spot being slightly warmer than the rest of the table if I keep dropping it on the same spot. And that's because since the table is taking stumbled over my words. Since the table is taking energy away from the marker, you could consider that to be work not conserved. So the table is exerting a force, it is doing work and taking energy away. Work not conserved turns mechanical energy into heat. So some of the energy is just becoming useless heat inside of the table and inside of the marker. So it still exists, it's just in a non-mechanical form and we can't see it anymore. So that's one other place that it goes. There's about 2 more places that the energy can commonly go. One of them's a lot harder to observe here because nothing's deforming. But if anyone has ever watched crash tests with cars, you'll see that they're able to get the crash test car up to a very high speed, and then it hits a brick wall and it comes to a stop almost immediately. What happens to the front of the car due to that? Yes. So it deforms a lot. And energy is used, work is done to cause that deformation. It takes energy to crunch the metal of the car. So some of the energy gets used up doing that sort of a thing. And the difference between an elastic object and an inelastic object is an inelastic object, like a car bumper, when it's deformed, is unable to go back to normal. The car bumper is metal and it just stays that way. An elastic object, rather than just that energy getting used up, forcing the bumper to compress, the elastic object stores the energy and then releases it again. So in an inelastic collision, some of the energy gets used up causing deformation in either of the objects. And that is actually why car crashes are designed to be inelastic. If you were in an elastic car crash, that means that all the kinetic energy that was present before the collision maintains throughout the collision, which means the collision has a lot more energy. You bounce off of the other car's bumper, which is really bad on the human body, because that means both cars are then accelerating a lot in a short amount of time. And this type of a collision would increase whiplash a bunch. Car crashes are designed to be inelastic on purpose. The reason you have a bumper is not so that it looks nice, it's so that that takes the impact, that takes in the energy and gets deformed, so that your neck doesn't.
So the kinetic energy from an inelastic collision just goes to deforming the object.
It goes to deforming the object, it goes into thermal energy inside of the objects, and there's one other place that it goes. So go ahead and have those 2 points written in the back of your head. There's just one more. There we go. I was trying to see if I could lead you to it, but sound is just moving air, and so you don't really see it. You don't really pay attention to it, but there is air involved in this collision. Like you're pushing air out of the way to cause this to happen, and so in an inelastic collision, a lot of the energy actually goes into the air and makes the air move, which you hear as sound. So inelastic collisions tend to be really noisy, like car crashes, because some of the energy, more so than in an elastic collision, gets dumped into the air, making the air shake, which you register as hearing. So there's lots of places that this energy goes, and I bring this up to remind you that the energy still exists. It cannot be destroyed. It had to go somewhere. It is just no longer kinetic energy in the objects we were looking at. So the law of conservation of energy still works. It's no longer in the form we were expecting. So in an inelastic collision, the energy just gets wasted into all these other states. This is different to an elastic collision, because in that type of a collision, the energy that went into the deformation of the objects is then able to be released again. It doesn't go away. It's still a mechanical kinetic form. And so in an elastic collision, the kinetic energy is also conserved in addition to the momentum. So, like I have on the other board over there, in an elastic collision, the objects will bounce off of each other. Rather than sticking together, they will spring off of one another. Now, how that looks will depend on the system. Sometimes the first object might stop and the second object will start moving. Sometimes they might bounce off in separate directions. Sometimes they'll still be moving in the same direction. It just depends on the system. But as long as there is a bounce involved and they don't join together, that is some type of an elastic collision. There was elastic interactions going on. And in that type of a collision, the kinetic energy is conserved in addition to the momentum. Everyone all right with the difference so far? Okay. So those are the two types of collisions thus far. This just summarizes all the assumptions that you can make. The bottom is an extra cheat code that I'll show you how to use later. Don't pay attention to the bottom one just yet. Right now, we're in an elastic collision. These are the two assumptions that you can assume. So previously, in the inelastic question that we did over here, we began only with the assumption that total momentum initial would equal total momentum final. But if the collision is inelastic, I keep stumbling over my words today, I'm sorry. If the collision is elastic, you can also start with this assumption, with this equation. The total kinetic energy initial must be the same as the total kinetic energy final. So So you now have, the reason we started with an inelastic collision is because since there's only one assumption that you can make, problems tend to be simpler. While an elastic collision, you have more starting points, which means more options. Often you need to use both of them concurrently. So in elastic questions, you tend to end up in a two equations, two unknowns type scenario, where you have to use both of these assumptions to get to your final answer. So we started off with the simpler one, and now we're going to do some examples of the harder one. So all of your momentum collision questions will begin like this, but some of them, the elastic ones, can also begin with this. All right? Any questions so far? Okay. If no one has any questions, we're gonna start a question at least. I'm gonna help you guys through this one. So, this is going to be an example of an elastic collision. This is the kind that you don't want to be in if you are, this is the kind of collision you don't want to be in. It's more energetic, that means it's worse on your neck. So, two discs of equal mass are going to hit, and they're going to have a perfectly elastic collision. What that means is, in reality, not every collision is perfectly elastic. There are certain degrees to which a collision can be elastic or inelastic. The more kinetic energy is conserved, the more elastic the collision is. In this equation, we're going to assume that all kinetic energy is conserved, and so that would make it perfectly elastic. But in real life, very rarely do you keep all of the kinetic energy in any collision, even the more elastic ones. If you've ever had a bouncy ball, like one of the super balls, and dropped it, not thrown it, but dropped it, it's never going to bounce back up to the same height. It's always going to bounce up lower and lower each time. And that's because even really elastic objects still lose a little bit of energy in a collision. The more energy it conserves, the more elastic the collision is considered to be. For these questions, you will either be told it is perfectly elastic, in which case you can assume that all of the kinetic energy is maintained, or you'll be told the degree to which it is elastic. You might be told that 90% of the kinetic energy is maintained. And you'll be given all the parameters you need for the question. Don't worry. So, these two disks, one is orange, one is blue, are going to collide, and they have equal mass, and the collision is going to be perfectly elastic. We can assume that all of the kinetic energy is maintained. The blue disk is initially moving at 5 meters per second. The orange disk is initially stationary. They have the same mass, and I had one more point and I forgot what it was. Anyway. So, again, every collision always has a beginning state and an after state. So you should draw each step separately. Up here, I've already got it drawn out. The before state has the blue disk moving. The orange disk is stationary. We don't know their masses, but we do know that their masses are identical. So I've just written mass m in both disks. Now, after the collision, the problem tells us that both of these objects are going to be moving. Now, everyone's played pool before, right? Now, because pool balls are round, it's very hard to actually get them to do what you want them to do in a collision, because when two round surfaces collide, unless it's a dead-on perfectly centered collision where it actually, that's the only time it's actually going to bounce back and forth in a straight line. Since these are round objects, if you're even a centimeter off, they're both going to take off in different directions. Everyone's observed that playing pool or any game with colliding round objects. All right, so since these disks are round, and if realistically speaking, they're not going to collide straight on, what's going to happen is they're both going to be moving after the collision. So energy and momentum from the first mass has transferred into the second mass, and now they are both going to be moving afterwards. They're both going to take off in separate directions. Now the question does tell us what directions they are moving in. The blue disk is going to be moving at 37 degrees up from the axis it was originally moving in. And the orange disk is going to be moving at 90 degrees from the direction the blue disk is moving in. So we know that the angle between them is a right angle, and therefore if this is 37 degrees, this would have to be how much? My orange marker. Thank you. Gesundheit. I almost wrote 37 again. So, we know the direction that both of these disks are going to shoot off in. We do not know the magnitude of their velocity. The point of the question is to find their speeds, but we at least know what directions they're going to be moving in. So that is what is happening before the collision and then after the collision. Now, because this is an elastic collision, the problem tells us it is, so we can make these assumptions. We know that the total momentum has to be conserved from start to finish, and the total kinetic energy has to be conserved from start to finish. So that is the setup here. I will work this one with you guys because since it's an angled question, I want to show you how it is done. I never find the marker I want to use. That's fine. So, we have our two assumptions here. Now, we need to start filling in blanks here. We need to start looking at the momentum and the kinetic energy before this collision happens, and then those same things after the collision happens. So I'm actually going to start with the kinetic energy for a very specific reason. So examining the kinetic energy of this initial system, where is all the energy before the collision happens? All right. The blue disk is the only one that is moving, so it has all of the kinetic energy to start with. So 1/2 times the mass of the blue disk times the velocity initial of the blue disk squared. That's the only object with energy initially. So that's the only source of energy to begin with. So this is the entire energy initial. Afterwards, both objects are moving at some different unknown final velocity. So 1/2 times mass blue times velocity of final of blue squared, and 1/2 times mass orange plus velocity final orange squared. So that is describing the energy present in the system. Now, looking at this, there's a couple things that we can go ahead and do to simplify this statement a little bit. Every single one of the terms that we currently have written up here has a 1/2 in front of it and the mass of the object within it. Since every single term has the 1/2, we can divide 1/2 away from everything. It can just cancel on every single term and go away completely. Does that algebra make sense? So that's just one less thing that we have to look at completely. And the problem also tells us that the mass of both objects is identical. They both have the same mass, which means that mass B and mass O are the same, meaning that every single term has the same mass attached to it, which means that can cancel out too. Because we can just divide that out like we did the 1/2. So what that leaves us with is the blue disk's initial velocity squared must be equal to the blue disk's final velocity squared plus the orange disk's final velocity squared. I would write it in your notebook like this because there are cases where the mass does not cancel out. Write the whole thing in, and then for this example, you can cross it out and make sure it's in your notebook where you can see it and look back at it later. Now, this were the assumptions we made based on kinetic energy. Are we able to solve for velocity from this step alone?
No.
No. Yes.
Can you also cancel out the squared, or is that not?
You cannot. You cannot. That is because on this side there is one term that is squared. On this side there are two separate terms that are being squared and then added together.
Okay.
I suppose you could simplify this to B initial B equals the square root of VFB squared plus VFO squared. But you'd have to do that by taking the square root of both sides, and that plus there in the middle, the fact that you're adding two things together before taking the square root means that it doesn't just cancel out. This is a fine place to start, though, if you want to keep it like this. I wouldn't recommend it, though, for a specific reason. So we know velocity initial of the blue disk. We don't know the velocity final of either of the two disks, because that's what we're trying to find. So this is one equation with two unknowns in it. We cannot get what we want with just this at the moment. So since that's all the information we can get from the kinetic energy assumption, now we need to start looking at momentum. So we need to examine the momentum of both disks before and after. Now initially, object 1, disk blue, is the only one with momentum. So kind of like before, that's going to be the only momentum that carries through. And then afterwards, they both have momentum. Some of the momentum from object 1 transferred into object 2. The problem here is the two objects are now moving in different axes. Momentum is a vector, meaning it cares about direction. Kinetic energy isn't a vector. So when we're solving with kinetic energy, it doesn't matter that these things are moving in two different directions. Because in the kinetic energy formula, the velocity vector gets squared, direction goes away. Kinetic energy is a scalar, so direction doesn't matter. But momentum is still a vector. So the direction still matters, meaning that we have to factor in direction when we are looking at each of these vectors. So our initial momentum is in the x-axis. The blue disk is only moving forwards in the positive x. So if we look at the initial momentum of the blue disk, so that would be the blue disk's mass times the blue disk's initial velocity. This momentum is only in the x-axis, meaning that we can only compare this to the x momentums of each object after the collision. And since these are vectors, we have to divide them up into their components. So the hypotenuse of the blue disk's final velocity is V1F, V blue F rather, and it is at a 37-degree angle upwards from the horizontal. So what is the trig statement that'll tell us what the x leg is equivalent to? Very good, cosine. So V blue final cosine of 37 is the x leg of this triangle. And subsequently, the orange final times cosine of 53 is the x component of this triangle. Is everyone following? Because I'm getting a couple different facial expressions right now. Okay. Again, because our initial momentum is only in the x-axis, we have to separate this up when we are examining momentum later. So, momentum initial. This is all in the x-axis that wasn't in any other axis. Afterwards, the blue disk its mass times its x velocity, and the other momentum currently in the x-axis is the orange mass and its horizontal component. So that's just their masses times the components that we found looking at the trigonometry. Now we know the angles, we know cosine 37, we know cosine 37, we know cosine 53, so these are just constants. And because all the masses are the same, and every term has the same mass attached to it, those can divide out again. So we're left with velocity initial blue, which we know is 5 from the question, equals velocity blue final times cosine of 37 plus velocity orange final times cosine of 53. So that's just examining the x-axis of the momentum. We now have two equations with the same two unknowns in them. So with these two equations that we now have, we can solve for both of our velocities now, using two equations, two unknowns. Is everyone okay getting to this point? And does everyone understand what you would have to do next?
Substitution.
Correct. Now, this is an interesting case where we can actually get a third equation with the same two formulas in it, and then you only have to use two of the three. Because this is only the x momentum of each object, but there's also the y-axis to look at, because each of them has a y component after the collision. If we look at the y-axis, after the collision, each object has a y component, and that would use sines instead of cosines. So where before we used cosine to find the x's, we would use sine to find the y's. So that's after the collision where they both have a y velocity. But what is the y momentum in the initial stage? 0. There is no y momentum initially. So the initial y momentum that these need to add up to is 0. There was no y momentum initially. Afterwards, they do have y momentum, but because there initially was 0, these two need to add up back to 0. So they cancel out. That makes this a third equation that you have access to. It has the same two unknowns in it. So between these three equations we have here, there's two unknowns in each of them. You can pick any two of these three to then use in your two equations, two unknowns, to solve for the final velocity of each disk. So we get 2 from momentum because momentum is a vector and direction matters. But direction doesn't matter for kinetic energy, so we only get 1 out of that. But any 2 of these 3, you can combine it, do 2 equations, 2 unknowns to find the 2 variables left in both of them. Does that follow? Everyone good on that? Okay. And again, I ask this because I legitimately want to answer your questions if you have them. Does anyone have any questions about how we got to this point? Or what this means in terms of the physics?
So do we use Y or what?
You can. There's 3 different equations that we can get from these 2 statements. You only need 2 of the 3 to find the variables you want. 2 equations, 2 unknowns. There's 3 different equations you can pick from. You just need 2 of them to be able to find the variables you need. But I wanted to show you all of them because this case specifically is a unique scenario that you should at least be familiar with because there's questions like it on your homework. A very common example that you'll see in textbooks is a case where 2 people are standing stationary on ice. So initially they have no momentum, but then they push off from each other. And so they both start sliding apart. In that collision, there was initially no momentum, but afterwards, each person has momentum. What that means is, since momentum is a vector, and since the 2 momentums afterwards are in opposite directions, the momentum of each person must have an equal and opposite magnitude so that it adds back up to the original 0. So you can get situations where your initial momentum is nothing, and the afterwards does have momentum, but they still have to add back up to nothing. Like how initially there was no y momentum, and afterwards the net sum of the y momentum is still 0 because they cancel out. They're just the same magnitude in opposite directions. Momentum is a vector, so you do have to consider those things. I know the homework, I don't know if the homework has a specific example where people are on ice, but there is definitely an example where someone is floating through space, and it's the same kind of a case there. If you are floating through space, and you throw something away from yourself, you initially had no momentum. But in that collision, now both of you have momentum in different directions, both you and whatever you threw.
So can you cancel out the mass and then the Y equation too?
Yes, you can. If you divide everything here by m, divide this by m, it cancels, divide this by m, it cancels, 0 divided by m is still 0. Which is why the problem never gave you mass, because no matter which 2 of these 3 you look at, it just cancels out. That won't always be the case, so in your notes I'd recommend writing in the m's and then just crossing over them for this specific example so that you do have it in your notes. But then, yes, in order to move on, you just need to solve 2 of these 3. And what I would recommend is actually this one and this one, because they have the fewest terms in them. And I will do that with you guys so that we can all get the number before we move on. So we have velocity initial squared, which is 5, equals velocity blue final squared plus velocity orange final squared. So this is the kinetic energy assumption that we made. And I'm going to choose to use the momentum y assumption that we made. That is 0 equals v blue final times sine of 37 plus the orange final times sine of 53. If I rearrange this, I can get negative VBF times sine of 37 equals VOF times sine of 3, divide this over, and you get negative VBF equals VOF sine of 53 over sine 37. These are constants. You can divide this and just find a number. Who put this can in my way? So you can plug this in instead of VBF. Might want to carry the negative over, sorry. Plug this in instead of VBF up here, then everything is in terms of VOF. You can solve for VOF. Get a number, and then plug it back in down here.
Can you write that in something else? I cannot read that.
The green is the problem?
Yeah. I can't see it.
Yeah, no problem. Is the red visible?
Yeah.
Red on top of green. This is turning into early Christmas. Can this be red? I know the two colors isn't causing any issues. Okay. So can someone go ahead and solve for sine of 53 over sine of 37 for me? 'Cause I can't do that in my head. 1.33. Thank you. So that means that VBF is equal to negative 1.33 times VOF. A lot of different facial expressions. How's everyone doing?
So we're only using two equations right now, right?
Yes. You only need, since each one has two unknowns, and they all have the same two unknowns, you only need to use two of them in conjunction with each other. I was just showing that you could use any of the three, whichever two you find first. I'm using these two because the fact that there's a 0 in this one is convenient, and this one has fewer terms in it. Now, using this equation, we've arrived at VBF equals negative 1.3 times VOF. We can take this, pull it up here instead of VBF. So 5 squared equals negative 1.33 times VOF squared plus VOF squared. Running out of room. 5 squared would be, someone tell me 1.33 squared. Thank you. The negative gets squared, so it goes away. So we have 1.77 VOF squared plus VOF squared. You can distribute a VOF squared out from these two terms, and that'll give you 2.77 times VOF squared. Should I show all those steps?
Sure.
All right, might as well then. I'm going to start erasing this question to make space. But, okay. Is everyone at least understand getting from here to here? Yes?
I'm still trying to write down the equations.
These ones?
I'm on the third one right now. I just got that one.
Okay, that's fine.
I'm just a little.
Okay, so this equation is this one. I just brought this term over. Then I just divided sine of 37 over to the other side to get VBF by itself. So that's all this is.
Divide sine 37.
Correct. So the sine of 37 is now on the denominator over here. And since sine of 53 and sine of 37 are just numbers, they're integers you can find, not integers, they're numbers you can find, you plug this into your calculator, it's just equal to 1.33.
Why would VBF become positive whenever you divide it?
I just brought the negative over with the sine of 37.
Okay.
The negative you can, as long as everything is being multiplied, I can just bring the negative back over when I want. But the negative doesn't really matter because when we square this up here, it goes away. So just to have more space, I'm bringing this over here. 5 squared is 25. That's equal to both of these terms have a VOF squared in them. So you can use the distributive property to bring the VOF squared onto the outside. 1.77 times VOF, if you pull the VOF out, is just 1.77. VOF squared divided by VOF squared is 1. Everyone okay with that distribution? So therefore, we go down to the next line, VOF squared times 2.77. Just add in the 1 and divide both sides by 2.77 equals VOF squared. And then take the square root. You should get VOF, the final velocity of the orange disk.
3.
Thank you, yes, my notes confirm that. Well done. So the final velocity of the orange disk, the magnitude of its velocity, is 3 meters per second at its 53-degree angle. I know that's a lot of work. I'm doing a lot of talking and pointing. If you have any questions, please ask them. Any confusion at all as to how we got to this point? So what you can then do with this number, you just plug it in for VOF. So 25 equals VBF squared plus 3 squared. That would be 9. Bring 9 over. And yes.
I'm having a hard time figuring out where the +1 came from.
Okay. So what I did here is both of these terms on the right side have a VOF squared in them.
Yeah.
So that means you can use the distributive property to pull the VOF squared out and just leave the other numbers behind. So this term is 1.77 times VOF squared. So when you pull the VOF squared out, it leaves behind the 1.77.
Okay. Yeah.
This term is just VOF squared. So if you pull the VOF squared out, it leaves a 1 behind, because this is, you could think of this as 1 times VOF squared, because you can't leave a 0 behind.
Yeah.
Because that would just get rid of the number completely. So algebraically, there's a 1 that's left here because you just divided it by itself, and that becomes 1. So that's where this came from. And then they add together to be 2.77, and then you get about 3 as your answer. And because I've seen these numbers before, if that's 3 and this is 5, this one turns out to be 4. Yes.
How'd you get from 1.33 to 1.77?
Ah.
Square?
Yes, this whole, okay, so the VBF is squared. So everything that we plug in instead of VBF gets squared. So this is all inside of these parentheses that then become squared.
Okay, so why does it still say squared at the bottom? Like, just below it, when it's 1.77 VOF squared.
Right. So we have to square every term in here, and there's 2 terms in here. One of them is the negative 1.33, which when squared becomes positive 1.77. And when you square the VOF, you get VOF squared. If we don't know it, we have to leave it like that. So again, take that, put it there. The VF, everyone should get about 4. Does everyone concur? All right. So the VF is 4. And this particular example is admittedly tricky because of the angles. Which is why I wanted to do this one with you, because this is one of the harder types that you encounter, because things get knocked around at weird angles. Some of the homework questions are within a single axis instead of 2. That means that you can't, that you wouldn't get 2 formulas out of the momentum assumption, because everything's only in one axis. So that means there's less work in those types, which is why I wanted to do the harder one with you guys, so that you could see it, because the same basic principles apply between all of them. I have one of the simpler examples next. I'd like to show that to you guys, see how you guys are able to handle it on your own, or working together. Before we get to that, again, does anyone have any questions about the one we just did? And does anyone need water? Yes.
Yeah, why did you find the VDF? I thought we already found it right over there.
Excuse me. We did find VBF. It's equal to 1.33 times VOF. And if VOF is 3, if you put the 3 over there, you get 4 for VBF. I guess technically you get -4. That just means that they're in different directions. Oh, I see the problem now. Yeah, negative sign is fine. Sorry, I'm confusing myself. Alright. Seems like whenever I suggest a water break, most people go for a phone break, which is fine. I mean, yeah, I got people I need to keep in touch with. But also I'm talking a lot, so I gotta keep my throat from going out. Okay, just to poll everybody while we're resting for a minute, are the differences between the 2 collision types making sense? Mostly. Okay. The next problem is simpler. So that'll be a good test of how you guys are able to do it. Working together. You guys can work with each other on this one. Don't worry about that. After this lecture, we will have covered all the topics that everyone needs to do their homework, which means you could have it done by Sunday. I'm probably going to push it back a day or 2 anyway, just because I wasn't here. We started this entirely in this week, except for the video lectures. So I might give you guys just another couple of days to ask some questions if you have any. I'll try to be in the office Monday so you can come by even if you don't have class. I know me being gone, through a monkey wrench and a few things, so I'm trying to be accommodating there. Okay, so I'm going to go ahead and show you guys the next example so that we can get started on it. This is to see how you guys are able to do it as a team. This is a single axis question. This problem had 2 axes, the next one only has 1 axis. So it is easier by itself. 2 cars named Kit and Nemesis Prime are driving straight towards each other. Does anyone know the names of, does anyone recognize the names of these cars? Okay, this is Kit, Knight Rider's car, and this is Nemesis Prime, Optimus Prime's evil twin. Yes.
I knew that from like the Benchwarmers movie. Like that's
Oh, yeah.
car's name.
Really?
Yeah.
Huh. I mean, I just knew it because my parents watched Knight Rider growing up. So, ultimately though, the point is two separate cars are driving towards each other. And they have two different masses, but they have the same initial velocity. Normally, car crashes are designed to be inelastic. You want a car crash to be inelastic, but for this one, we're just going to assume that it is perfectly elastic just to see what happens. So, you know the mass of each vehicle. That stays the same throughout. That doesn't change. And you know the initial velocity of both vehicles. They are both moving towards each other at 45 meters per second. What I would like you to do is tell me the velocity of each vehicle after this elastic collision. Please discuss, work together, ask me questions.
Are they going, so they're,
Moving towards each other.
and they go straight back?
You don't actually know that for certain.
Okay.
The weird thing with elastic collisions is when the two objects have different masses, the collisions get really chaotic. Sometimes you get a case where they will just bounce off of each other completely. Sometimes you get a case where one of them will stop and the other will keep going. Sometimes you'll get a case where they end up both going in the same direction because one just had way more momentum than the other. You don't know what direction each one is going to move in until you do the math, but you do know that they are initially moving towards each other. So that will affect the positive and negative signs on a few things. Okay. You know what? If it'll help everyone get started, I'll go ahead and draw the picture with you guys. Give you guys the picture to start from as a unit. Okay. Every collision is going to have a before, I'll put the before on top, and an after. Beforehand, you have the smaller Knight Rider car with a mass of 400 kilograms. I can't talk. How are you guys today? And an initial velocity of 45 meters per second in the positive direction. And it is heading towards the much larger tanker truck with a mass of 2,000 kilograms. Muy largo. Why did I write that number again? Heading at 45 meters per second towards Kit. Now, directions matter, because momentum is a vector, velocity is a vector. So, you have to consider that they are moving in opposite directions. One of these velocities needs a negative sign on it. And so we will just go ahead and say, in our little corner grid system here, to the right is positive x. Therefore, the truck is driving in the negative x direction. Your signs are going to be very important here because that will also tell you what direction each car is moving after the collision, besides just their just the magnitude of their velocities. So that's before the collision. After the collision, the cars won't stick together because this is an inelastic collision. They will still move separately. The issue is that you don't actually know what their velocities are or even what direction they're going to be moving in. You know they will both be moving, and you do not know that their velocities will be the same. They're two different final velocities. The issue is you don't know how fast either goes afterwards or their direction. But you do know their masses. Those will stay the same. So again, you could always start analyzing the initial statement and setting it equal to what you know about the final statement. And since this is elastic, you need to do that for both momentum and kinetic energy. So as a unit, start analyzing the initial momentum and the initial kinetic energy and set it equal to afterwards. I will put that on the back of this whiteboard. How's everyone doing so far? Has everyone at least analyzed the momentum and kinetic energy of each of the systems before and after? Okay. Do you want me to show you?
Yes.
Okay. So, because it is an elastic collision, we have our two assumptions that we can start from. Total momentum initial must be equal to total momentum final. Total kinetic energy initial must be equal to total kinetic energy final. Initially, we have two masses, each moving with their different velocities. Momentum is a vector, direction matters. We need to plug in the negative 45 meters per second for the truck. That's equal to each of their masses times their final velocity, which we don't know yet.
Now, because momentum matters, because direction matters with momentum, that means that the net momentum of the system is actually in the negative direction. Since the truck has more mass and since they're moving at the same velocity, the net momentum is going to be in the negative direction. So the net momentum is a negative number. The negative only implies in the negative direction. And then that's still equal to the sum of each of their final momentums. I'll let that a 1.